All right, today we're putting on our detective hats and opening up a massive cosmic cold case. What happened in the very first fraction of a second of our universe's existence? We're going to see how scientists use evidence from the cosmos to figure out which stories about our origins could actually be true. Let's start the investigation. I mean, this is the ultimate question, isn't it? Before the first stars, before atoms even existed, the entire universe that we can see was crammed into a space smaller than a single proton. So what was going on in there? What were the rules? To have any hope of figuring that out, we need a theory that actually matches the clues the universe has left behind for us. So the main framework for this whole investigation is an idea called cosmic inflation. You can kind of think of it as the universe taking one single gigantic breath. In a flash, it went from subatomic to enormous. This incredible expansion explains a lot, like why the universe is so big and smooth, and it also planted the tiny seeds that would, billions of years later, grow into all the galaxies we see today. Now, inflation isn't just one theory. It's more like a family of suspects. And our prime suspect for today is one of the simplest, most elegant versions, known as chaotic inflation. For a long, long time, this was a top contender. It's clean, it's straightforward, but as we're about to see, its alibi has a few pretty big holes in it. Every good detective story needs a twist, right? Well, here's ours. When we actually compare what simple chaotic inflation predicts to the real evidence we've gathered from the sky, we find a huge problem. The theory tells a very specific story, but the facts are telling us something completely different. Okay, this slide lays the whole problem out perfectly. The theory predicts that this incredibly violent expansion should have shaken the fabric of spacetime, creating a powerful storm of gravitational waves, kind of like a cosmic rumble left over from the beginning. Scientists measure the strength of this rumble with a number called R. Chaotic inflation says R should be pretty big, greater than 0.14, but our best evidence from the amazing Planck satellite shows that the universe is actually incredibly quiet. The real value for R is less than 0.07. The suspect's story and the evidence from the crime scene, they just don't line up. So is that it? Is the case closed on chaotic inflation? Well, not quite. What if the problem isn't the suspect itself, but the laws of physics as we understand them? Maybe at the insane energies of the Big Bang, gravity itself just worked a little differently. This is our new lead in the case. So this new lead comes to us from a pretty wild area of physics called string theory. It's a proposed tweak to Einstein's theory of gravity, and it's called the Gauss-Bonnet term. Think of it as a special rule for gravity that only turns on under the most extreme conditions you can possibly imagine, like the first moment of the universe. It connects space-time itself to the energy field that was driving inflation, and the strength of that connection is a value we call beta. The key thing is, this new piece of the puzzle could change the whole story. And this is really the heart of our investigation now. Can adding this new piece of physics, this Gauss-Bonnet term, fix chaotic inflation's alibi and make it match the evidence from the Planck satellite? Could this be the one missing detail that makes the suspect's story finally check out? So how do we find out? Well, scientists can't just guess. They have to put this new, modified theory through a really tough interrogation, hitting it from every angle to see if it actually holds up. And this interrogation has 3 crucial steps. First, you check it against the crime scene evidence. Do its new predictions match the Planck data? Second, you check the follow-through. You see, after inflation ends, the universe has to reheat and smoothly transition into the hot Big Bang we know and love. Does that part of the story make sense? And third, does it play by the rules? You have to check that the theory doesn't just break down and start giving you nonsense answers at high energies. It's a pass/fail test. All right, the interrogation is done. The lab results are back. Let's take a look at the final verdict on our modified theory. And this table just lays it all out so clearly. As we knew, standard chaotic inflation is pretty much out. Now, what if we applied this new gravity twist to a different inflation model, like Higgs inflation? Well, that fails even worse. But then, look at that third line. One specific version of chaotic inflation with our new Gauss-Bonnet twist. It can work. It can actually produce predictions that match the data. A second version, though, is still a bit shaky. So the final verdict isn't innocent. It's more like viable, but only under very heavy constraints. And that right there is the key takeaway. This new twist on gravity isn't some get-out-of-jail-free card. It only works if its properties, like that coupling strength beta, land within a really, really narrow range of possibilities. Those tests we talked about? especially the reheating check, they act like an incredibly fine-toothed comb, getting rid of almost all the possibilities. So just how narrow is that range? Well, the analysis of how the universe reheats puts a hardcore upper limit on the strength of this new physics. That beta value has to be less than about 1,000. If it were any stronger, the whole story of how the universe transitioned from inflation to the hot Big Bang just falls apart. And you don't have to take my word for it. This quote from the researchers themselves really says it all. They say that these reheating constraints are so tight that they create a clear tension with the values you'd need to match the data. It's kind of like finding a key that fits the lock, but only if you hold it at this one very specific, almost impossible angle. So what does this whole cosmic detective story tell us? Not just about the Big Bang, but about how science itself actually works. It shows us that science moves forward, not just by proving theories right, but often by proving them wrong, or in this case, by showing that they can only be right under incredibly specific circumstances. We didn't solve the mystery of the Big Bang today, but what we did do is take a whole universe of possibilities and shrink it down to just a tiny, focused sliver. The case isn't closed, but the detectives now know exactly where they need to look next. And that leaves us with a final, just mind-blowing thought. The fact that we can use light from the dawn of time to conduct this kind of detailed interrogation of the universe's very first moment is absolutely astounding. It really makes you wonder what other cosmic secrets are out there, just waiting for the right evidence and the right detectives to come along and finally crack the case.